All right, this is it. This is what you've all been waiting for. Learning about staging and scoring sleep studies. This is where the fun is, I think. You become the guy at the screen in the Matrix, knowing what's happening just by looking at some squiggles on the monitor. So, right now, we're just talking about being awake and being asleep. And if asleep, what kind of sleep? Nothing right now about scoring, which means counting how many obstructive or central respiratory events or leg movements a patient has. Just sleep, what kind of sleep, and wake. When you're watching this, take your time. Yes, this is some of the most important stuff, and it's going to sound incredibly weird, but that's just because you've never talked about this stuff before. Just take good notes, take your time, and try to draw the different kinds of figures that you will see. And once we start to put it all together, I promise it will make sense. I was exactly in the same position you were when I was in sleep school. At one point, I knew nothing about the brain and thought it would be nearly impossible to learn how to read all the waves. But I really wanted to be able to do it, so I just worked at it and I got pretty good at it. With these presentations, I will share with you what I look for in sleep studies, which is really the same thing everybody else looks for, but I'll show you exactly what to look for and why. If you know why something is happening, there's a good chance you'll remember how it happens. One other note. There are a lot of figures and diagrams. You should draw these, especially what the different waves look like. They won't be perfect, but do your best. This will really cement what these waves are like in your head. Before we can understand the rules of staging sleep, we need to learn the basic waveforms for the EEG. The majority of staging sleep is based off the EEG, the brain waves. There are other things that can help, like the chin EMG and the EOG, and the respirations, but the EEG is really what to look at. We look for certain waveforms in specific areas. That's why we are recording at least 3 different regions of the brain at once. We record the frontal region with F3 and F4, the central region with C3 and C4, and the occipital region, which is at the back of the head, with O1 and O2. We'll talk about which waveforms show up the best in which leads later. Sometimes the EEG may not show enough clues to definitively stage sleep, so we can also use the EOG, the chin EMG, and even the respiration to assist in staging sleep. A derivation is just a single line or channel in an EEG. It represents a single view on what's going on with that part of the brain electrically. A collection of derivations is called a montage. There are many different montages, and they include the basic sleep study EEG channels like the Fs, the Cs, and the Os. Parasomnia channels add FP1, FP2, T6, and T7, and CZ. Full head hookups just adds the rest of the 1020 hookup locations. When we look at an EEG, the signals are differential, meaning that we are taking the difference between the voltage of one spot to the next. In our case, we are just looking at the voltage differences in one location and comparing it to a place that has virtually no electrical activity. The mastoid bone behind the ear, also known as M1 or M2, those are our references. You put it on a bone, the bone has no electricity going through it at all, so that serves as our baseline. We call looking at EEG this way a referenced differential EEG. Other EEG montages will link electrodes up in a way that will tell us where the electricity is heading, where seizures are happening, also called the focus of a seizure, which there are many different ways you can compare voltages in EEG. But we're just focused on what's happening, for example, in F4. We tie that to a bone location, mastoid M1 or M2, and that serves as the 0.0 electrical baseline, and we just see what's happening in F4. This is the AASM's recommended and alternative setup for EEG montages. Don't be silly, use the recommended. If you have to, you can switch F4 to F3, C4 to C3, and O2 to O1. We have both sides of the brain for many reasons. We'll talk about that too. EEG, electroencephalography, that's brain waves. Those are the brain waves that we look at. No matter what part of the brain we're looking at, we measure all the waves the same. We calculate waves by their frequency, their amplitude, as well as their morphology, or how the wave appears. Initially, as beginner sleep technologists, you may rely on counting the waves within the seconds line, like on a graph. Eventually, you'll just know what delta waves or alpha waves or theta waves look like instead of needing to count them. Frequency means how many times something happens in 1 second, and EEG waves occur in a spectrum from low to high. And I like to remember the range of frequencies by thinking D-tab, delta, theta, alpha, beta. That puts these waves in order from least to greatest, occurring from the least in 1 second to occurring the most in 1 second. We measure how many waves occur in a second by counting trough to trough or peak to peak. Troughs being the low points of waves, peaks being high points. We express these values in hertz, which means cycles or waves per second. If a wave deflects or goes up and down less than 3 times in 1 second, we would consider those waves delta waves. If the waves occur between 4 and 7 times a second, those are theta. Waves occurring 8 to 13 times per second are alpha waves, and beta waves occur more than 13 times per second, which is pretty fast for brain activity and sleep. If you look online or in different textbooks, there might be very slight different values for the margins between these ranges. Like delta may start at 0.5 hertz and end at 2.99 hertz instead of 3. Theta may go from 4 to 7.99 hertz. It all still fits within the range. They just may be listed differently. I guess 7.99 would be more precise. This is something they may do on the BRPT exam. List values within the range and expect you to know the full range and then pick the closest answer to the real values. Amplitude refers to the height between a trough and a peak, or a peak and a trough of a wave. Amplitude is expressed in microvolts, meaning how much actual electricity in that part of the brain is moving, also known as a discharge. The only wave for adult sleep that has a required amplitude to score are delta waves, and they have to be 75 microvolts from peak to trough. Otherwise, there are no other requirements. The exam will ask you questions like, what is the amplitude requirement for alpha waves or theta waves? And there aren't any, at least not yet. The scoring manual does like to add more rules like amplitude and frequencies that weren't there before, but right now, delta waves are the only ones you need to know like. Here's a super handy reference to what all the waveform properties are. Let's see. Amplitude refers to the height of waves. For instance, this whole thing is the amplitude. This is from the peak to the resting point. This is also the electrical baseline. This is negative voltage and amplitude. So when we're looking at sleep or electricity, vertically going up and down, this is voltage. We also call it amplitude or the height. All of that is the same thing. Going horizontally, that is time. So the wave is going up, down, up, down, up, down through time. And depending on how many times that happens in 1 second, that would be hertz. So waves don't look like this in real life, but this shows you what you're going to count. You may hear certain terms like crest instead of peak. Do you know what we call this up and down red wave? This is a sinusoidal wave, and that just means it goes up and down smoothly like this. But yes, these are the peaks of the waves, the highest point or the highest amplitude, highest voltage, lowest voltage or negative voltage. Here's a nice reference table to what the different waves can look like. Remember, some ranges in different books may vary, but they are all generally the same. Notice the little key that has a box and says 1 second. That is standard. All these pictures are to scale. We'll talk more about these ranges in the next slide. But Check this out. This is alpha. In between this second, if we start right here, 1, we have to go up and down. That is a wave. 1, 2, 3, 4, 5, maybe 6, 7, 8, 9, 10. It's about 11 or 12, which is right in the frequency of alpha. Beta, it's going to be greater. Check out, you can see some daylight, some white in between these waves. That's space. These have no space in between them. These waves are so fast. These are beta. They're so fast you can't even count them. They kind of blur together. Here's theta. The amplitude on this is pretty high. Theta usually isn't this high, but I wanted you to see it well. This is the spacing, though. Let's see. 1, 2, 3, 4, 5. So that's about 4.5 to 5 waves per second, which is in the range of theta. Then we've got delta. And here it says less than 4. So, let's see. 1, 2, maybe. But the other thing is we have to have an amplitude, and we don't really have that on here. This is just for getting you to know what the morphology looks like. How do the waves appear? Alpha is considered a faster frequency between 8 and 13 hertz, and it's seen the best in the occipital channels 01 and 02. There's an actual piece of the anatomy that serves as an electronic oscillator. An oscillator is something that goes in a circle, and that circle makes something go on and off. And that's what these alpha waves are. The up and down, up and down, up and down. The waves are given off when a person is awake and with their eyes closed. These can also be seen when a person arouses from sleep. When the person opens their eyes, this alpha disappears. It's pretty neat, I think. We also call the wave that appears when someone is awake with their eyes open the PDR, or posterior dominant rhythm. And we need to start calling alpha the PDR, because that's what it is. That's what the real, term for what it's called when someone is awake with their eyes closed. Because children, and you'll learn this later in PSG 212 for pediatrics, but children have a slower frequency of PDR, and it's not alpha. So we don't say when a child awakes, oh, there's alpha. No, they don't have alpha. It's slower. It's more like theta. So instead of saying it's alpha and just PDR for children, we're going to call it PDR for everybody. But you should know that the posterior dominant rhythm in adults is alpha. So let's break that down. PDR, posterior dominant rhythm. Posterior means rear, which is where the occipital lobe is, at the back of the brain. Dominant meaning which wave comes through the most. And rhythm meaning how often something happens or doesn't happen. Approximately 90% of adults show alpha as their PDR. This changes when we get into pediatric stuff next year, and I told you about that. For now, just know that the PDR stands for posterior dominant rhythm, and for alpha, for adults, it's alpha, which we see when someone is awake with their eyes closed. Commonly, in EEG studies, one of the characteristics that a technologist will document is at which frequency the PDR occurs. Moving on to theta waves. These occur 4 to 7 times per second. In sleep, we will find theta waves occurring with something we call low amplitude mixed frequency, or LAMF. Low amplitude means the waves aren't very tall, nor they're not very big, and mixed frequency means there's no dominant frequency like alpha. That happens the whole time. Theta waves are seen in stages non-REM 1, non-REM 2, and REM sleep. For adult sleep, there's no set amplitude requirements for low amplitude mixed frequency patterns, except for children. just think of low amplitude as relatively low amplitude. This is another prime example of the same thing being called many different names. Delta, delta sleep, delta wave sleep, slow wave sleep, and non-REM 3 sleep. They're all the same thing when it comes to sleep technologists staging sleep. The reason we don't really consider anything less than 0.5 hertz a slow wave is because waves don't really occur that slowly or incrementally below 0.5, so we typically just refer to them as 0.5 to 2 hertz. Although you can say slow waves occur between 0.1 and 2 hertz. And some books say they go all the way up to 4. Slow waves have an amplitude. In fact, they do go to 4. It's supposed to be 0.5 to 4. Know that. Slow, let's just to make you understand. 0.5 to 4. Some places will say 3.99 to 4. All right. Slow waves have the amplitude requirement of 75 microvolts. So that means from here to here, this has to measure 75. And this is the sign for microvolt. And that is from trough to peak or peak to trough. These have to be slow waves all the way down and up. Sometimes we have other waveforms that just aren't frequencies, like delta or alpha. We don't really have much beta activity when it comes to sleep, except when we see sleep spindles, which are an indicator for non-REM 2 sleep. When we look at an EEG, it's set up so that you can't really see anything faster than 13 hertz. So they can appear very, very close together and thick and dark with very little space between them. This is why a movement artifact or leg movements looks just like a big black block, because muscle fibers twitch incredibly fast, and on an EEG setup they look just like a big black blob. Beta waves are just slow enough that we can generally detect a tiny bit of space, and this is like a really nice tracing, but right in the middle you can't see any light there. You can maybe see some right here, but these are kind of big. I've blown it up so that you can see it. Central sleep spindles show up the best in the central derivation, C3 and C4. Spindles generally appear between 12 and 14 hertz, specifically. Vertex sharp waves, sometimes called V waves, show up during non-REM 1 sleep. They are quick up and down deflections that stay on top of the baseline. Usually they are in the theta frequency range, 4 to 7 hertz. I'm going to expound upon these in a couple slides because they do resemble a different wave, and I can explain the difference in between the two so you can tell. Vertex sharp waves are not a requirement for scoring non-REM 1, but it is a feature, and so it can give you extra data and for confirming that it is in 1. Remember in EEG when the wave deflects upwards, that is a negative deflection. If the wave deflects or goes down, that is a positive deflection. EEG is backwards. So, a K complex shows, a sharp upwards deflection, which represents a negative voltage or discharge, followed by a slower downward deflection representing positive voltage. These typically last half a second. This right here is just repolarization. That's just the baseline going back up because we had this huge wave, and K complexes can be very big. That this baseline has been kind of skewed. EEG works with like square root formulas so that it's going to come back to the baseline, but because this wave, which is much different from what it had been, the baseline is slowly coming back to normal. You don't really have to know that, but just know that a K complex is this really straight, see how straight that is, and then it's pretty straight here, and then there's waves riding on this repolarization. So just know that that's the K complex. They typically last half a second. They are a strong indicator of non-REM2 sleep and are maximally seen in the frontal regions. A big thing I notice in sleep staging are getting K-complexes and vertex sharp waves mixed up, the last waves we saw, which is really easy to do. There is a difference between the two, however. The K-complex's downward deflection goes all the way through the baseline and creeps back up. The vertex sharp waves will just stay on top. I'll demonstrate this on the next slide. Here we go. I have superimposed an imaginary baseline that shows the difference between vertex sharp waves and K-complexes. The K-complex downward deflection goes through the baseline right there, all the way down and comes back. This is the vertex sharp wave, and it stays on top of the baseline. That's the difference between both of those waves. The electrooculogram, or EOG, tracks eye movements. We have several different kinds of eye movements we can see, and they all assist in staging sleep. We have E1 and E2, like the EEG wires. They are referenced to a mastoid. It doesn't really matter which electrodes are referenced to the opposite side of the head, but it is something that the BRPT continues to do, so I would try and learn it that way. So E1 to M2, E2 to M1, those are referencing both eyes to the opposite side of the head. The reference serves as a baseline with no electricity, so the deflections we see are just purely from the eyes. That's what the eyes are doing electrically. Here we go. Check out the EOG here. We have E1 up and down and up and down, and we have E2 up and down, up and down. These are slow rolling eye movements. They are slowly deflecting up and down from each other. These are common for non-REM1 sleep and for sleep onset, up and down waves. Those are slow rolling eye movements. You can see those, in one, but also being very drowsy. Here we see what technologists call eye clicks. These are rapid eye movements. Right here, there, and these are the eye movements. Remember, like the K-complex, they're so big that it has to take time to go back to baseline. Then it happens again. We've got some more there, and there. That does not appear to be one because I don't see anything on the other side. These happen rapidly and spontaneously without a pattern, unlike slow rolling eye movements. Slow rolling eye movements, you can tell where they're going to go, up and down and up and down. Rapid eye movements can be seen while awake or in REM sleep. This epoch is in REM. You can tell by the low chin tone. That is a very fine line. It's not very black at all. There is no muscle tension in any of the wires, actually. Those are very clear tracings. And you would see more muscle tension and more darkness in these wires when someone is awake. Here we go. Here's rapid eye movements while the patient is awake. Look how much, this is the EEG. This is probably an O. That is all alpha right there. You see that? That's great alpha looking stuff right there. And here are eye movements. Look at that. Eye movements. This patient, and see, look at that chin tone too. This is the chin. It's not that very straight, fine line. It's got a lot more noise to it, and that's an active chin. I would call this dynamic, meaning it changes. It's not the same. Here are eye blinks. This is the EOG. These are the EEG. This looks like low amplitude mixed frequency. There's mixed frequency EEG. It looks pretty low amplitude. When these 2 points are coming together, these are the EOG, E1, E2. Blink, 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 blink. We also know the patient is awake. Well, number one, they're blinking. 2, look at the chin tone. There are these bursts of EMG, and it's all over the place. It gets bigger, smaller, bigger, smaller, bigger, smaller. So that is someone is awake. Okay, check out these blue lines. This just looks like a jumbled mess. But those blue lines are E1 and E2. And those are actually delta waves being captured through the eye channel electrodes, E1 and E2. These eyes aren't moving. Those aren't eye movements because our eyes move together. They can't, except for crossing your eyes, they don't move. They certainly don't move like that. But because these brain waves are so big, they're being picked up by E1 and E2. This you technically call this EEG artifact because we are not trying to see brain waves in the eye channels, but this is normal and you can't fix it. There's nothing to do about it. You just know that these aren't eye movements, they're just EEG. If you remember the slides we just looked at, we had a very thin line when the patient was in REM, and it was thicker and dynamic while awake. We call that the activation of muscles tone. The very thin line during REM is what we may consider the lowest chin tone during the night, which typically occurs during REM. The highest chin tone would usually occur when the patient is awake, and some chin tone is normally present during non-REM sleep. Here is that chin tone again. Very fine line. There's little tiny blips, but that's just because it's so fine that it has to show something. Check this out. Do you see all the spindles? Here's some. They're very fast, like right there. You can't really see any spine. These are great. Nice spindles right there, right there, right there. We have decent chin tone. It's about moderate. It stays pretty much the same. It's not really going any higher than that. So this is non-REM. Specifically, it's non-REM 2 because it's got the spindles. There aren't any delta waves. Here's wake. This is the classic one for chin and chin tone. Look how much tone there is. That's what that is. So these are all the typical channels that you will see in a sleep study. And all the programs you use or montages you'll see later do not strictly have all these channels in this order. But the EOG and the EEG are typically at the top of the screen. And then the respiratory sensors and movement and stuff like that is seen at the bottom. The top is usually for sleep staging, and the bottom is usually for scoring events. So starting off with EEG, you have to have the 3 EEG channels, an F, a C, and an O. So why do we have more than one electrode for those lobes? Many reasons. One is so that if the primary electrode comes off or breaks or stops sending a signal, you can reference to the other wire. For instance, if you lose F3, you can change that in the study to F4. If you lose F4, then you need to go in and fix it. Fixing wires when they come off may be up to your judgment, but you should do what the policy and procedure manual tells you. Also, you can have all 6 EEG channels up and you can see both sides of the head at one time. This can assist in spotting seizure activity and helping tell which side of the brain it's happening on. If you've only got one side going on, you can't see the other side where stuff might be happening. You can also see other defects if the waves are not synchronous on both sides, going up or down at the same time as synchronous. All these wires are referenced to a mastoid electrode, or M1 or M2. It doesn't really matter, like I've said earlier. Also, if you lose M1 or M2, you can then re-reference the electrodes to the other M. There are also 2 other extra wires you have to use to do an EEG, and that's a reference and a ground wire. Those don't show up on the PSG because they just have to be there as a total overall electrical baseline. That helps it. And you have to have 4 wires to see alternating current electricity waveforms, which is what our brain works on, alternating current. Next, we have the eye electrodes, E1 to M2 and E2 to M1. Sometimes, if the programs are fancy, these groups of inputs will be different colors, like the EEG could be black, the eyes blue, and the heartbeat red. It's not always like that. Next, you get the chin EMG wires. Most labs have 3 wires that connect to make 2 chin channels. The electrode that's put on the very center of the chin is usually the hardest to keep on, and is usually the first to fall off. So re-referencing chin 1 to chin 3 is pretty common. You will also have limb leads, usually 1 channel for the left and 1 for the right. The EKG, or the heartbeat, the heart rhythm, may use 2 or 3 electrodes like the chin. Having more than 1 EKG channel can provide different views of the electrical pathways of the heart and detect different abnormalities. Also, know that the EKG is mandatory in PSGs and all EEG tests. The reason being, EKG artifact can show up in the EEG and they can resemble sharp waves. Now, we want to know if a sharp waves in the EEG is real or if it's just EKG artifact. So we can check and see if the waves in the EEG and EKG line up to verify its validity. For the respiratory channels, you have a separate channel for the nasal cannula, which represents nasal pressure airflow. The thermistor records temperature airflow. The snore microphone records vibrations from the throat, so snores and vocalizations will show up. 1 for each of the rib belts, abdomen, and chest, and a channel for pulse oximetry, which tracks oxygen. That's a lot of stuff. Okay, so you can see the very left side are all the gray boxes. Those are the channels. These are the channels from like that. And these go from left to right. F1 or F4, C4, O2. They go like that. This is time. This is 30 seconds from left to right. We call that an epoch, 30 seconds. Remember, all setups won't look like this. Some might have the eyes and the chin channels at the top, and then the EEG, and then the chin. It's all the same stuff, and you'll get used to knowing which is which because you'll just know kind of what the eye movements are going to look like and stuff like that. The top 3 channels are our 3 EEG channels, F4, C4, and O2. The next channel is the chin lead. Sometimes there might be 2, in which case you would need 3 wires. The chin wires do not need a mastoid reference, no M1 or M2. Only the EEG and EOG are needing those. Next down are the 2 blue wires. Those are the right and left eye, E1 and E2. The next channel is just a dedicated pulse channel, and the pulse is derived either from the pulse oximetry or the EKG, so you don't have to add any wires for this channel. Next one down is EKG. Again, you may have 3 EKG wires, which would have the capability of showing 2 channels. The EKG also do not require a mastoid reference. This record specifically was recorded using the program from Compumetics. In my opinion, Compumetics has some of the cleanest and prettiest EEG wave tracings of all the other programs. Compumetics has the capability to look at a top layer and a bottom layer. You can kind of see this line right here, and then it says 30 seconds, and then at the top here it would say 30 seconds 2. You could change like this just to 2 minutes so that you could see this in 30 seconds and this in 2 minutes. That way you could keep track of what's happening respiratorily. That's one way to watch the study go, but I think it's always best to time lock both layers and look at the data in either 30 seconds or just 2 minutes. So here, the second tier begins with the right and left leg limb leads. Wow, right and left leg limb leads. That's hard. Then the next is the snore microphone. After that is the thermistor. Then the nasal pressure, PTAF. Sometimes it's called PTAF, and that stands for pressure transducer airflow. The effort belts for the chest and abdomen, and finally, the pulse oximetry for the oxygen. Now let's check this one out. It's the same montage, but there are an extra 9 EEG channels from here down to there. Those are all EEG channels. The rest is the same. So don't get intimidated by all the different channels. Look at what's on the side, and you can figure out what you're looking at. That's it for now. We will dive into staging sleep in the next presentations. It would be most advantageous of you to start knowing the ins and outs of the scoring manual. The beginning talks about the stuff that's required to go into a study, and then the rules for scoring and staging follow. Pay attention to the first section, too, because some of that will be on the exam. We'll cover that some other time.